this video, I am going to discuss about the motional EMF in rotating a conducting rod in a uniform magnetic field. अगर कोई रॉड किसी यूनिफॉर्म मैग्नेटिक फील्ड में जब रोटेट किया जाएगा अबाउट एनी एक्सिस, then how much induced EMF is set up across its end. Let OP is a conducting rod of length L is rotating in a magnetic field, and in this case here the rod is always perpendicular to this magnetic field. It means if suppose magnetic field is perpendicular to the plane of paper directed downward, so this one is a magnetic field perpendicular to the plane of paper directed downward, and this one is a rod which rotated. So always this magnetic field is perpendicular to the length of this conducting rod. So let a conducting rod OP of length L is rotating in this magnetic field B, which is perpendicular to this conducting rod about the point O. This conducting rod is rotated in this magnetic field about the point O. Suppose at any instant the position of this rod is OP. किसी समय मान लेते हैं इस रॉड की पोजीशन इस मैग्नेटिक फील्ड में क्या है, OP, and after time dt its rotate and its position comes from OP to OQ. इसका मतलब dt टाइम में ये रॉड रोटेट करके OP से कहां पहुंच जाता है, OQ पे. In what time, dt. And when it rotates from OP to OQ, suppose it moves through what angular displacement, d theta. And suppose this rod OP is rotated about the angular velocity, constant angular velocity omega. हम मान लेते हैं कि ये कंडक्टिंग रॉड OP जो है वो कांस्टेंट एंगुलर वेलोसिटी ओमेगा से इस मैग्नेटिक फील्ड में अबाउट द पॉइंट O क्या कर रहा है, रोटेट कर रहा है. Then our aim is to find how much electric potential or induced EMF is set up across the end of this conductor. So for this purpose, first you will find out in time dt, what is the area covered by this conducting rod. So area covered by this conducting rod is area of OPQ. This one is simply you will take for a small d theta. This one is nearly you can measure straight. So this will becomes in a form of a triangle. So you will take the area of OPQ. It means in time dt, the area covered by this conducting rod dA is equal to, how can you find? Area is equal to half into OP into PQ. You can imagine here. You can take this PQ is nearly a straight line for the small d theta. So you can take half OP into PQ. Now a question arises here, what is the PQ? PQ is in a form of arc, and all of you know angle is equal to arc upon radius. Angle is equal to arc upon radius. So arc is equal to, you can write here, angle into radius. Angle is how much? D theta. And what is the radius? When it will be rotate about the point O, then what will be the radius of this circular path? This becomes radius is equal to OP, which is equal to the L. So you can write here arc is equal to radius L into angle is how much here? D theta. So here you can write this one is L into D theta. And now area shift in time interval dt is given by half OP is how much? L into PQ is how much here? L d theta. And now you will get here half L square d theta. This one is d theta. And we know that magnetic flux phi is equal to how much here? BA. And in this case, the rate of change of magnetic flux linked with this rod. So how can we find the rate of change of magnetic flux? That one is d phi upon dt. This one is rate of change of magnetic flux is equal to B into dA upon dt. क्यों? क्योंकि यहाँ टाइम के साथ एरिया स्ट्रिप्ड बाय दिस रॉड ये कितनी एरिया शिफ्ट करेगी ये चेंज हो रहा है. इवन द मैग्नेटिक फील्ड B is remain constant. So we can take here d phi upon dt is equal to B dA upon dt. And dA upon dt is equal to what here? Half L square d theta. So we can write here B into d dt of, you can write here half L square and here d theta. And finally we can write here, the rate of change of magnetic flux d phi upon dt, is equal to half L square we will take out, B is already here, so B into half L square, and now what is left? D theta upon dt. Or we can say rate of change of magnetic flux linked with this rod d phi upon dt is equal to half B L square. Here d theta upon dt is what? What is d theta? Angular displacement. And d theta upon dt will give what here? Rate of change of angular displacement. And rate of change of angular displacement is called angular velocity. And this one is here half B omega L square omega. So d phi upon dt is equal to half B L square into omega. One more thing. By Faraday's law, Faraday's first law, you know induced EMF E is equal to minus d phi upon dt. But when you will take the magnitude of the induced EMF, means mod E, so at that time you will write here d phi upon dt. So the magnitude of this induced EMF or E, I am writing its magnitude is equal to d phi upon dt, and this d phi upon dt is equal to how much here? Half B L square omega. It means in this case the induced EMF across the end of the rod is given by half B L square omega. And this formula is very important to solve the numerical problem, especially in the case when any conducting rod is rotating in a magnetic field. So the motional EMF induced across the end of the conductor, whose magnitude is given by mod E is equal to half B L square omega, where mod E means I am taking the magnitude of it here. Now there are the two important points. Suppose if we consider a conducting rod PQ of length L is rotated in a uniform magnetic field B with constant angular velocity omega about an axis passes through the point O and perpendicular to its length. What I am saying here, first notice what here. Suppose a conducting rod PQ of length L is rotating with the constant angular velocity omega in magnetic field B about the middle point O, and suppose this point O is about which it is rotating, it is perpendicular to length. So in this case the potential difference between the point P and Q, क्योंकि यहाँ पे ये O के about move कर रहा है ये P पूरा rod, so this one will be fixed and this one is rotated. So in this case the potential develop at point P as well as point Q, and in this case the potential difference between P and Q, you can write Vp minus Vq is equal to G. It means the net potential difference between point P and Q is equal to G. This first point. Second point is, in this case, if we consider the potential difference between middle point and one end of the rod, what I am saying here, if we consider the potential difference between the middle point and one end, any one end, suppose I am taking here VO minus VQ. So in this case, when you will consider only half of length about this point, potential difference between O and Q, तो आप assume कर सकते हैं कि now this rod of length L by 2 is rotating in this magnetic field with the angular velocity omega about the point O. And already you have calculated the formula for this one. Half B L square omega. So in this case, potential difference between middle point and any one of the end VO minus VQ is given by half B. At place of L, you will take L by 2 whole square and into omega. And finally you will get here half B L square by 4 into omega. It means VO minus VQ is equal to B L square omega by 8. Or finally you can say VO minus VQ is equal to 1 by 8 B L square omega. And remember this, if O is at higher potential than Q, then potential difference is VO minus VQ. And in this case, this rod will be rotated anti-clockwise. And if P is at higher potential than O, if the midpoint O is at higher potential, then this rod will be rotated in anti-clockwise. But if the potential at any end is greater than the O, then this rod will be moved in clockwise direction. So in this way, you can find out the potential difference across point O or P or O and Q or across PQ in. Now, next topic is self-induction. As it is clear, self-induction means in this case, I will consider one coil only. Means only one coil. Suppose this one is one coil. And don't think like this one here, both coils together here. I am taking one coil, this one is case 1 and this one is case 2 in two possible cases here. Suppose this one is one coil and this one is a rheostat, source of current, battery, and this one is a key, battery, and this one is rheostat. And with the help of this rheostat, we can change the current in this coil. इस rheostat की मदद से हम इस सर्किट में करंट को क्या कर सकते हैं, इस कॉइल में चेंज कर सकते हैं, चाहे करंट को बढ़ा सकते हैं या करंट को घटा सकते हैं. So here two cases I am considering here. First case here, when main current increased, it means in this case here, with the help of this rheostat, the main current in this coil is increasing. And here, when main current is decreasing, in this case, then what will be the induced current developed in this one here? So actually, self-induction is a phenomena of electromagnetic induction in which on changing the current in a coil, an opposing EMF is developed in each turn of the coil. And this phenomena is called what here? This phenomena is called self-induction. And if the coil be closed, then that induced EMF is the cause of the induced current. Once again, listen here. Self-induction is what here? The phenomena of electromagnetic induction in which on changing the current in a coil, an opposing EMF is induced in every turn of the coil. This phenomena is called what here? Self-induction. And the opposing EMF which is developed in this one here, since the coil is closed, so that opposing EMF is also cause of the opposing current, or you can say induced current here. And here that induced EMF or that opposing EMF is called back EMF also here. So in this case, you can say, suppose in this coil, with the help of this rheostat, when we increase the current, so when the main current increases, so a current carrying coil behaves like a magnet. It means the magnetic line of forces passes through itself, it changes. And when the magnetic line of forces passes through itself, it changes here, then an induced EMF is set up as well as induced current because coil is closed. And since main current is increasing, so the induced current tends to oppose the increase of the current. And for this purpose, if this main current is going from left to right, so induced current will take place from right to left. It's vice versa. If with the help of the rheostat, when we decrease the current, when main current decreases, अगर ये main current decrease की जाएगी तो again a induced EMF is set up here as well as the induced current, but the direction of that induced current is such as which tends to increase the main current, क्योंकि मेन करंट जब घटेगी तो इसमें जो इंड्यूस करंट होगा वो चाहेगा कि मेन करंट को बढ़ाएं, but for this purpose in this case the induced current will be takes place in the direction of the main current. यहां पे इंड्यूस करंट मेन करंट के डायरेक्शन में हो गया, इसलिए क्योंकि मेन करंट घट रही है तो ये इंड्यूस करंट मेन करंट के घटने का अपोज करेगा, तो इसलिए इसी डायरेक्शन में चलकर उसको बढ़ाना चाहेगा। और यहां पे मेन करंट बढ़ रही है तो इससे पास होने मैग्नेटिक फ्लक्स चेंज होगी, इंड्यूस ईएमएफ डेवलप होगा एज वेल एज इंड्यूस करंट भी डेवलप होगी, लेकिन वो इंड्यूस करंट मेन करंट के बढ़ने का अपोज करेगा, इसलिए मेन करंट अगर लेफ्ट से राइट जा रही है तो इंड्यूस करंट इसका अपोज करेगा, राइट से लेफ्ट चलेगा। सो इन दिस वे यू कैन डिफाइन व्हाट इज सेल्फ इंडक्शन। सपोज if phi b is the magnetic flux linked with each turn of this coil and n with the number of turns in this coil, then the total magnetic flux linked through the whole coil is n phi b. And this total magnetic flux linked with whole coil is actually depends on what here? Current which is flows in it. जब तक करंट नहीं फ्लो करेगी तब तक इसमें से पास होने मैग्नेटिक फ्लक्स चेंज नहीं होगी। It means this total magnetic flux which is passes through this whole coil n phi b, this one is directly proportional to the current flow in it. And when we remove this proportionality constant, फिर से सुनिए, what is phi b? Phi b is the magnetic flux passes through each turn of the coil. Total number of turns in the coil n. For the total magnetic flux passes through the whole coil n phi b. And by definition this n phi b is directly proportional to what here? Current flow in it. जैसे जैसे इस करंट को बढ़ाया जाएगा टोटल मैग्नेटिक फ्लक्स भी क्या होगी? चेंज करेगी। एंड व्हेन वी रिमूव दिस प्रोपोर्शनलिटी कांस्टेंट तो यहां पर हम एक नया कांस्टेंट इंट्रोड्यूस करेंगे एंड दैट वन इज कॉल्ड L into I. This L is called where L is coefficient of self induction. इस L को क्या नाम दिया गया है? Coefficient of self induction. And from here you can say L is equal to n phi b upon I. And in this way you can find out the coefficient of self induction is equal to n phi b upon I. So simply n phi b is directly proportional to I. When we remove the proportionality constant, we introduce a new constant which is L, and n phi b is equal to Li, where L is called what here? Coefficient of self-induction. And in this case, and if on changing the current in the coil, जैसा मैंने बताया, on changing the current in the coil, an induced EMF is set up in the coil, and that induced EMF is called also back EMF. इस केस में so the induced EMF set up in the coil, how can we find? By Faraday's law, E is equal to minus n delta phi b upon delta t. In this way we can find out the induced EMF in a coil. And here E is equal to minus delta, you can write here n phi b upon delta t. And from here n phi b is equal to Li. So also we can write here E is equal to minus delta here L I upon delta T. This one. Or you can say E is equal to minus L, we can write here delta I upon delta T. I'll take outside here delta I upon delta T. So from here L is equal to minus E upon, we can write here delta I upon delta T. This one. L is equal to minus E delta I upon delta T. And if delta I upon delta T is equal to 1 ampere per second, then you can say coefficient of self-induction is numerically equal to E. Numerically equal to E means अगर हम इसका केवल मैग्नीट्यूड लेते, इस केस में माइनस नहीं लगाते तो मॉड का मतलब हम इसका क्या ले रहे हैं, केवल मैग्नीट्यूड ले रहे हैं। तो अगर डेल्टा आई अपॉन डेल्टा टी को क्या करते हैं 1 एम्पियर पर सेकंड लिखते, तो ये एल की वैल्यू किसके बराबर आती, आप लिखते ई के बराबर, न्यूमेरिकली ई के बराबर आती, तो एल इज इक्वल टू मॉड ई। नाउ हाउ कैन वी डिफाइन द कोएफिशिएंट ऑफ सेल्फ इंडक्शन, हम कोएफिशिएंट ऑफ सेल्फ इंडक्शन को कैसे डिफाइन कर सकते हैं, तो हाउ कैन यू डिफाइन द कोएफिशिएंट ऑफ सेल्फ इंडक्शन is numerically equal to induced EMF in a coil in which rate of change of current is 1 ampere per second. Again, listen here. The coefficient of self-induction of a coil is numerically equal to induced EMF in that coil when rate of change of current in that coil is 1 ampere per second. And if anybody asks to you what is the unit of L, तो यहां से आप देखिए यूनिट ऑफ L निकालेंगे क्या हो जाएगा, वोल्ट अपॉन एम्पियर अपॉन सेकेंड। यू कैन राइट वोल्ट सेकेंड पर एम्पियर एंड वोल्ट सेकेंड पर एम्पियर इज आल्सो कॉल्ड हेनरी। इट मींस द यूनिट ऑफ सेल्फ इंडक्शन इज व्हाट हियर, हेनरी। Since L is equal to minus E upon delta A upon delta T, लेकिन याद रखिएगा L की वैल्यू हमेशा पॉजिटिव आएगी जब आप सॉल्व करेंगे न्यूमेरिकल, L नेगेटिव नहीं आएगा। क्यों? क्योंकि आप डेल्टा I अपॉन डेल्टा T जब कैलकुलेट करेंगे तो ये वैल्यू नेगेटिव रहेगी और वो नेगेटिव क्या आ जाएगी, पॉजिटिव। तो L विल ऑलवेज व्हाट हियर, पॉजिटिव। तो द SI यूनिट ऑफ L इज हेनरी एंड 1 हेनरी इज इक्वल टू 1 वोल्ट upon ampere per second, and this one also you can write 1 volt second per ampere. So you can write 1 Henry is equal to 1 volt second per ampere, and 1 volt into second is also called vapor. So also you can write vapor per ampere. So in this way you can write the SI unit of coefficient of self-induction. The smaller unit of L like millihenry. So 1 millihenry is equal to 10 to the power minus 3 Henry. Suppose it is given the inductance of a coil is 1 millihenry. Millihenry means 10 to the power minus 3. 10 to the power minus 3. So microhenry, millihenry. In this way you can write what here is smaller unit of L. So dear student, today you go through the topic here what I have discussed. In the next video again I will give the next topic what here, coefficient means mutual induction, coefficient of mutual induction, and last topic is eddy current.